Okay, let's get started here. First of all, assignment number 2 is due on Friday at noon. With respect to the midterm here, right before class, I moved it to March 10th, and I was thinking that will be the date. The reason being because I know there's no class in here after us, and just to give you, let's say, 15 extra minutes for the exam, it's nice to have that available to us. But then when I came down here for class, I took a look at the schedule again and showed on Thursdays, at least where it's graphically shown, it shows that there's a class that comes in here like right at 12:30. But in terms of the text itself, it says 2 o'clock. Take a look at it after class today, you can see what I mean. So while I made this switch before class, I might switch it back to Thursday, because we should be ready this Thursday for the exam in terms of the material that we need to cover. And I had only switched it here to make sure that you would have, let's say, an extra 15 minutes if needed for the exam. So first of all, just to make sure, because I don't want to have to write 2 tests, are there any conflicts that by chance any of you may have for either of these days? That, maybe you're going to be at a conference and can't take the test? Okay, good. So anyway, I'll make a decision soon regarding exactly which date the test will be on. So Robert, we were just talking about the upcoming test here. Do you by chance have a conflict with either this date or this date for the test? Okay.
Not yet.
Nope. Good. So don't go out and try to schedule anything either. You say, oh, that looks like an interesting conference in Australia. I'm going to go to that one now. I guess I really don't like to have to write 2 tests if possible. Usually, at least for me, it takes about like 5 hours to write a test. So that means if I have to write one test and then a separate test, it's another 5 hours. Okay, so are there any questions before we get going here?
Yeah. For problem 2I on the homework,
Yep.
Just kind of gauging the efficiency of my code at this point, how long do you think that should take to run?
I think you're at least the 3rd student who's asked me
Okay.
that. And I will tell you, on my computer for n = 80, it took me about an hour.
Okay. I'm at an hour and a half, so.
Okay. Get a faster computer.
Yeah.
Well, yeah, I wanted to make sure that there was something that would be somewhat time consuming, because in a real situation it will be. And then eventually, once we get to using parallel processing and what's called high performance computing, where we can use multiple cores of a computer chip in terms of a processor on a computer, then that will allow us to knock that time down in a dramatic fashion. Any other questions? Okay. So I want to quickly get done with some stuff here so that we can move on to hypothesis testing. So we left off on the bottom page 66. We had just went through the a discussion again, the Monte Carlo simulations involving confidence intervals for sigma squared. And I want you just to look at it on your own. I wrote this nice little summarize function that will allow me to calculate both the estimated true confidence levels and also the estimated expected lengths. Please take a look at that on your own. The information that's here is basically what was on those plots that we saw before, so I'm not going to go over in detail. Okay, so now now this is outside this example. So just to make sure you realize this, and I think you see this from the assignment. This T star that we're calculating, let's say for every resample, T star itself is actually a discrete random variable. Okay, there's only a finite number of possible values that T star can take on. And you looked in the project about, well, what is the probability of essentially a particular T star? Now, something that you may not have noticed yet in the project, assignment, depending upon how far you are, is that when you look at the multinomial distribution aspect, there's a finite number of possible combinations of those counts. How many combinations are there? 2 times n, your sample size, minus 1, choose n minus 1. That's how many. I think it ends up being, I want to say it's like 100 and something.
126.
Okay. And so what this represents then is the number of unique resamples that one could have. Now, how do you actually go about proving that indeed that for any problem with a sample size of n, that's what you get? I often give that as actually an assignment for students. I just decided not to this year, so I'm just going to briefly describe it so you can see how it's done. If you have any of you heard of combinations with repetitions? Now, if you've taken combinatorics at UNO under Convolina, you should have heard that. A few students in class have done that. And this is just an application of combinations with repetitions. Now, if you haven't heard of those things before, you can take a look at page 15 of Casella and Berger, number 4. And basically, it shows you how you can do counting that takes into account that, some of you, in this case, as you've seen in the assignment, that some of your resamples are essentially the same. Okay? And it allows you to do, and it's a nice little way of doing that counting. So all of you have actually seen this in Stat 882 kind of class. You just may not have realized that, oh yeah, this is directly applicable to the bootstrap. Okay? So with respect to the air conditioning data then, that means we have 23 choose 11 different, we have 23 choose 11 unique resamples. Now each of these possible resamples could potentially have a different probability to it. Again, that probability comes from the multinomial distribution. Now, and so in the end, there's a little over 1 million possible different resamples. Or I'm sorry, a million possible different unique resamples. I need to be careful with how I'm saying this. If you ever want to know how to do a combination in R, it's the choose function. Okay, now since T star has a discrete distribution then, you may see this discreteness in various plots that you produce. It's not, usually, it's not necessarily something to be concerned about. And so I want to give you an example with the air conditioning data here. Hopefully someone's not printing off the lecture notes. Okay, so there's my data. Again, I just copied it in there just so that we could reference it. And what we see here is this really, really messy plot. But actually, it's not that bad after I explain it. So this is for the air conditioning data. This is a plot that's directly from Davis and Hinckley's book. On the x-axis, we have values of T star, where again, remember, we're calculating the mean for every single resample. So that's why it's called the bootstrap average. And then on the x-axis, on the y-axis here, we have S star divided by the square root of n. Well, what's the variance of a sample mean? Well, sigma squared sigma squared over n. So the estimated variance would be s squared over n. So then the standard deviation would be s divided by square root of n. And so this corresponds to something that we talked about earlier in the notes when we looked at how can we find a variance. Remember, we looked at vjack, we looked at vboot, and we said there might be cases where you could actually derive a closed form formula. And of course, for a mean, you can. And so it makes sense then if you were to calculate then the variance of, let's say, T star for each resample, well, just take S star divided by square root of n. So S, again, will be the sample standard deviation, the regular old formula that you've seen before this class, but now calculated for the resamples. Okay. So what we have here is a whole bunch of standard deviations and means plotted here. And obviously you can see that the standard deviation is a function of the mean. Ignore what you and so that's what's represented by the black dots for 999 resamples. Now ignore the blue lines. Okay? And remember that the largest value in our sample itself is 487, which is quite different from the rest. That's why we had a right skewed distribution. And so you can see how now 487 is affecting what T star is, and also what the sample standard deviation is as well. So for example, let me get my highlighter out here. So we can see that when 487 appears in a resample 4 times, that's what these dots correspond to. Get a new highlighter out. So when 487 appears in the sample 3 times, that's what these dots correspond to. So you see this banding there. And again, the reason why I'm pointing this out is that this is common when you use the bootstrap, the non-parametric bootstrap that is, because again, T star has a discrete distribution. This is not something to be alarmed about. And so it's interesting, you can all the way go down to when 487 appears in the resample 0 times, and all the way up to 6 times. Now let's take a look at the blue line as well. And you see basically banding within banding. So first of all, you see that that's a bad color. Let me just do it black here. No, I didn't get the black. Oh, we'll do purple. You see that blue circle around everything? Well, just ignore it. That shouldn't be there. Okay? Focus instead on what you see down here when 487 appears in the resample 0 times. Now, the second largest value in our sample is 230. And so what we see is another set of banding within the 487 appearing 0 time set of values. So for example, excuse me. So when, let's see, 230 appears 4 times, we're here. 230 appears 3 times, we're here, and so on. So we have bands within bands, and you see the same kind of pattern then appearing throughout. That's what this discreteness leads to. Now, when should you be concerned about discreteness like this? Well, maybe if you have, let's say, a lot less of these discrete, these bands, a lot less. And we'll talk about at the end of the bootstrap section, somewhat we'll talk about, well, when can that occur? When does a bootstrap not work? And also, and it all kind of comes down to what's called the smoothness of your statistic. So what that basically means, and I'll explain more later, an average is a smooth statistic, meaning that small changes in your data are not going to greatly affect what the statistic is. Now take a look at a case where maybe you are calculating an order statistic, or let's say the maximum possible value, that's your statistic. Now, that's a case where your statistic itself is not smooth. And small changes in your data perhaps could greatly affect stuff. And that's a case where the bootstrap will not work well. It's more than what I wanted to get into, but that's where we're headed. Okay, let's also now talk about some notation before we get to bootstrap hypothesis testing. There is 2 distinct sets of notation that people use often with the bootstrap when they're talking about probabilities and when you're using expected values. Okay. What we've been using so far is this notation. Let's say expected value of t given f. What that basically means is that your underlying y's come from the distribution f. And also expected value of t given f hat. What that basically means is, again, your y's are coming from now from the distribution of f hat. The reason why I use this notation was to emphasize the plug-in principle. And that's why people often use it. That's why people often usually introduce the bootstrap using that notation. Eventually, though, they tend to migrate to a different kind of notation, represented like this. Expected value star of t star is equivalent to the expected value of t given f hat. So what the star is emphasizing is our notation where we had y1 star, y2 star to represent values for my resample. And then the star on the expected value part is to emphasize that, okay, I'm working with f hat here. This notation, I think, is less confusing because when you have a t here, you're thinking, well, wait a second, maybe that should be t star. Because after all, we're always putting a star on our resamples. Well, you could do that, but essentially that notation is redundant and it's not as general. So that's why those notations are typically kept separate. Now, when I taught a whole course on the bootstrap, probably one of the most difficult things for students, especially at first, is the notation. To understand, okay, are my y's with respect to f hat, or are they with respect to f, or maybe even f hat star, for example. And I think what I actually did, I think the second time I taught it, I put together like a 3-page, or maybe it was 5-page notation sheet just to help out my students. You can go to my Bootstrap website for that course if you really want to see it. I don't think it's really necessary for what we do. But I at least wanted to point out this kind of notation, especially when you read the literature and you see people using the Bootstrap. Please understand that these notations mean the same thing. What's even more confusing is that if you read Davis and Hinckley and you don't know anything about the Bootstrap before you start reading it, they sometimes will use both sets of notation interchangeably. In fact, sometimes they will do it at the same time. They will use both sets. So they might put a T star even though you have an F hat in there. And surprisingly, when I took a corresponding course out of that book, I didn't notice it. My advisor didn't notice it. It's because we were so used to using the Bootstrap actually before we did this stuff. And then once we started teaching it to students with this book for the first time, then that's when the confusion started occurring. We were like, oh, that's not good. And especially, I won't dwell on this too much more. And especially, it's disappointing that we missed that because we actually did the JAZA book review for Davison and Hinckley. And we didn't put that in our book review. Oh well. So if you don't know what I mean by JAZA book review, a lot of the big journals will always have reviews of books at the end of an issue. And we were asked to do the book review for JAZA. Okay. So now let's talk about hypothesis testing with respect to the Bootstrap. I will admit that confidence intervals are actually easier than doing hypothesis testing with the Bootstrap. And the reason is this. In the non-Bootstrap world, before you started taking this course, whenever you did hypothesis testing, basically you had to derive some kind of statistic. Often we refer to as a test statistic. That test statistic's distribution needs to be known under the null hypothesis. So assuming the null hypothesis is true, this is what the distribution would be. Well, we essentially need to do the same thing here with the Bootstrap. But since we are using this plug-in principle, we need to plug in for, let's call it F0, the true distribution under the null hypothesis. We need to basically plug in for F0 with F hat 0. Okay, now the reason why that can be an issue is because when you observe your data, your original sample, is that data, does that reflect the null hypothesis? Is it under the null hypothesis? Maybe, maybe not. So what that means then is if you want to take resamples to do this hypothesis test, you are going to need to adjust your EDF so that it is actually representing the null hypothesis. What that means then is that you're going to have to adjust your observed sample so that the null hypothesis is true. That's the difficult part. Hold on a second. Okay, good. I did hit record. It's always a big fear of mine that I forget to hit record before I start. So anyway, there isn't, generally speaking, there isn't one way to make this adjustment. Often it's very problem dependent. So I might ask you to go do a hypothesis test for a mean. Well, how you adjust the data there is probably going to be totally different if you were to do, let's say, a likelihood ratio test for something. That's what makes this difficult. Okay, so speaking of a hypothesis test for a mean, your very first hypothesis test you probably ever saw. Let's take a look at how we can use the bootstrap for it, or how we can resample, first of all, I should say. So, mu is equal to mu 0. Mu 0 is some constant. That's my null hypothesis. The alternative is mu does not equal mu 0. What I'm going to do is adjust my data so that the null hypothesis is true. Adjust my actual sample. So I'm going to create what I call y tildes. So y tilde sub I is my ith adjusted data value. And what I'm going to do is take my original data value, y sub I, and subtract off y bar, or y. W-H-Y, not in terms of the word or the letter y. Why am I doing this with my y's? The reason is because notice that means now if you were to take the mean of yi minus y bar, that mean would be 0. All the yi minus y bars, that whole, if you were to add them up, divide by n, the mean would be 0. So I'm mean adjusting my data. And then I'm going to add back the hypothesized mean. Now my y tildes satisfy my null hypothesis. And I can resample directly from the y tildes. So essentially my f hat sub 0 here is the EDF of all my y tildes. Okay, let's go a step further. What should I calculate for every resample? Could someone give me in symbolic form what I should calculate for every resample? There's going to be a y in it. Excuse me? Well, it's not just y bar. Y tilde bar. Let's call it a star there too. So I need y tilde star bar. I need to calculate that for every single resample. And suppose I did a histogram. So here's my y tilde bar star. I don't know which order to say everything in sometimes. And I'm going to have a resample that, or a histogram that might look something like this. And we'll put a little right skewness on it. So, what this is representing is an estimate of my distribution of my statistic if the null hypothesis is true. Okay. Now, if I wanted to decide if I reject or not reject HO, what should I do next? Think of it in a graphical manner. Well, what do we typically do with hypothesis testing? We looked at our observed value of our test statistic from our original sample, and you look at how extreme is it relative to the distribution under the null hypothesis. So what would I use here? What statistic would I use with this histogram to decide if I want to reject or not reject? Not y tilde bar. So what we have here is, again, a representation of the distribution under the null hypothesis. This would be like your t distribution, for example. Okay? And then what do you calculate for your observed sample? The observed value of t, right? I'm not doing that here. Instead, I could calculate something else and still do a hypothesis test. What would that be? So I'm looking at what my I'm looking at what my statistic would be under the null hypothesis. We only adjusted our data so that we could get an estimate of the distribution under the null hypothesis. That was the only reason. So what do you think my statistic should be that I compare to this distribution? What?
Is it y tilde?
Not y tilde, no. What?
Normal z.
No.
T distribution.
No. Well, I guess you have weighted me out. Just simply y bar. Because we don't know, if this is under the null hypothesis or not. And so what we want to do is look at how extreme is y bar relative to my null hypothesis distribution. So if, let's say, my y bar ended up being right here, what do you think that means? Is that y bar extreme? Would you expect to get a y bar there if the null hypothesis was true? Or would you say, wait a second, that's kind of unusual? Yeah, it's kind of unusual. And so this just gets back into the basics of what you do with hypothesis testing. You look to see, well, you come up with some kind of distribution under the null hypothesis that will allow you to calculate a measure of extremeness. Is it reasonable to have your observed value of the test statistic or not? So if I have a y bar that ends up being, let's say, right about here, kind of in the middle, oh yeah, that seems reasonable. I got a lot of y tilde star bars there. Again, if I had, let's say, a y bar way out here, oh, that's not reasonable. I would never likely ever observe a y bar out that far if the null hypothesis was true. So that's how you do the test. Yes?
So we're not resampling to calculate y bar?
Well, y bar is the observed sample mean.
So,
And the only reason why we're resampling is to come up with some idea of what the distribution would be under the null hypothesis.
Oh, okay.
That's it. Now, how else could you do this test? Well, you can use a t-test statistic as well. We'll talk about this more later. You could calculate the regular old t-test statistic for each resample. The notation will get a little bit messy here, so that's why I'm not going to throw it up there right now. But you could calculate that for every single resample. and then also calculate for the observed data as well. And simply look at how extreme is your observed t-test statistic relative to what we estimate the distribution would be under the null hypothesis. That's it. Okay, so let's look at now what will be likely your second hypothesis test that you ever saw in your statistical careers. A test for difference of two means. So I have two groups, let's say group 1, group 2, or you could say two populations, population 1, population 2, and we're simply looking at are the means equal or not. There's actually a few different ways to go about doing the resampling in this kind of a case. So, approach number 1. This comes directly from Efron Tibshirani's book. Let's first of all label our data like this, where we have y11 down to y1 n sub 1. So we have a sample size of n1 from population 1. And then we have y21 down to y2 n sub 2. So we have a sample size of n2 from population number 2. And now what we do is we kind of follow the same idea that we saw with the hypothesis test for one mean in order to adjust our data so that the null hypothesis is reflected, and then we can resample directly from this adjusted data. So I'm going to let y tilde sub 1j, so the 1 there is for group 1, be equal to your original observed value, subtract off the observed mean for group 1. So notice how it has, now this first part here has a mean essentially of 0. And then we add back the overall sample mean across both groups. Because if they have exactly the same mean, it would make sense to estimate that mean with essentially their combined average value. And then with group 2, I essentially do the same thing. Take the data value, subtract off the sample mean for group 2, and add back the overall mean. And now what I can do is I can perform what's called a stratified bootstrap, or I'm sorry, stratified resampling approach, where I resample my y tilde 1 sub j's first, put that into my group 1 for my resample, and then I sample the y tilde 2 sub j's and put that into my group 2 for my resample. And I repeat this, let's say capital R times. So with a stratified resampling approach, you can do that with the boot function. There is an argument called strat that allows you to do that. You'll see an example of how to do that later, hopefully today, in the context of a different problem. So what would you use, what would you calculate then as a test statistic for every single resample? What would be the simplest thing that you could do? So y tilde star bar sub 1 minus y tilde star bar sub 2. You get a histogram of all those values, and that will tell you then what the null hypothesis distribution would be. And then you calculate y bar 1 minus y bar 2 and look at its relative position to that null hypothesis distribution. You could also use the regular old t-test statistic that you've seen before for these kinds of problems too. Okay, so that's approach number 1. It makes sense relative to what we saw for testing for one mean. Let's look at approach number 2. Simply combine both samples into one. Resample N1 observations with replacement to form you could say a new group 1, and then resample and 2 more observations with replacement to form a new group 2 of data. So notice, if you think of the original data values itself, some from group 2 could end up being in group 1 for a resample, and vice versa. Okay? Well, why? Why would you do this as a way to resample under the null hypothesis? Well, essentially what you're doing is you're assuming that essentially the data is coming from the same population. If they have the same population, of course, they have the same mean. Okay? That's why this is a reasonable approach to do. But by doing that, though, you're actually making an additional assumption, and it was kind of loose to what I was saying about the same population. So the hypothesis that you're actually testing is something stronger than just simply, are the means equal? Because by this sampling approach, you're actually assuming that they have the same population under the null hypothesis. So let's let F1 be the CDF for group 1, and I'm going to call that H sub y. And then F2, the CDF for group 2, let's call it H sub y minus delta. So in other words, a simple shift of your data. Maybe delta could be 2, for example. And so what the actual hypotheses are that you're testing is this. HL delta is equal to 0. The populations are the same. HA delta does not equal 0, meaning that they are just have some kind of shift. So notice if they have some kind of shift like that, are the means equal? No, because the data has been shifted by a certain number of units, delta units. Yeah.
Should the N1 and N2 be necessarily the same?
No. No. No restrictions on that at all. Now, when you do your resampling, you have to make sure that you always take for your group 1 N1 observations, and for group 2 N2 observations. But N1 and N2 don't have to be exactly the same. Note that this is actually also assuming then equal variances, because of course a simple shift of your data by delta units, that's not affecting a variance at all. So while this is a valid approach, and some people actually even use it, is actually there's more assumptions behind it than what we had with the previous approach. We will actually see a little bit later on in our bootstrap section another place where this exact same thing comes up in the context of a permutation test. Approach number 3. Let's suppose our data actually arises through the following simple linear model. You've seen models like this before, back in Stat 970. Y sub ij, so again, the ith group, or you could say ith treatment if you really wanted to, and the jth observation in that ith group is equal to a mean that's dependent upon which treatment or group you're talking about, plus standard deviation times your error term, where this error term has a mean of 0, variance of 1. So notice this allows you to have non-constant variance. All of you should have seen a simple model like this in like a course like 970. Now this is, again, assuming that your data comes about like this. And that's an assumption, because why couldn't I also think of my data coming along or coming about this way? A multiplicative model. It could. Or maybe I just put a star there, or a times there. My data could come about like this. So this is an assumption. So because of this, I wouldn't necessarily call this a fully non-parametric approach, unlike approach number 1 and approach number 2. I would prefer to call this a semi-parametric approach, but some people would still call it non-parametric, because I'm not necessarily specifying an underlying distribution for my y's. Now look what the null hypothesis means here. Again, mu1 will be equal to mu2. So in other words, under the null hypothesis, my data is actually arising through this model, where I just simply have a mu there. If you want to, you can actually calculate residuals from this model. Please note the little typo in the notes there, where you see this blue here. I forgot a sigma squared sub I. So I can calculate a regular old residual. So the y minus its estimated value, and this is under the null hypothesis now, divided by the estimated variance of what's in the numerator, essentially. Okay. Now these e's actually, these residuals actually have the same distribution. You know, remember back to your days when you've done some simple regression models. You know, you often did like a plot of your residuals, maybe a histogram to examine various assumptions of your model. A key aspect of those residuals was they essentially have the same distribution to them, because you've taken into account the mean, you've taken into account the variance. Well, these e's essentially have the same distribution to them. So because of that, now, and because notice how I've incorporated the null hypothesis in there, I can actually resample my e's in order to generate a new set of y's that are under the null hypothesis. This is how it's done. So let's let E star sub ij denote a resampled E sub ij. So again, the I corresponds to the group number, the J corresponds to the particular observation. I'll talk about that more shortly. These E stars are actually randomly, just simply resample from all your E's. It doesn't matter which group, it doesn't matter which observation. They're resampled from all the E's because the E's all have exactly the same distribution. Once you get those E stars, put them back in your model like you had before. Include from your original sample itself an estimate of the standard deviation, and also from your original sample itself include an estimate of your overall mean. Put that all together, and that's how you get a Y star. Once you get the Y star, you can calculate your statistics of interest. Like the difference between the two sample means. Now, to emphasize this point of these E stars, because it can be kind of confusing, let's suppose that N1 is equal to 3 and N2 is equal to 2. So I have an overall sample size of 6. So that means I'm going to have E11, E12, E13, E21, E22. Now, what my E stars then is just simply resampling from those guys. So for example, one possible resample could be, and I'm just going to start off with my labeling in order here. E star 11 could be E13. E star 12 could be E21. Notice how they have different group numbers there. Essentially, you just take when you resample your E's, you're just putting them back and assigning the labels to them. And the easiest way is the first one that you get from all your E's, let's call that the 1, 1. The second one that you get from all your E's, let's call that 1, 2, and so on. And this is how you do your resampling. Now, the reason why this approach is so important, and one reason why I bring this up now, is because this is very, very closely related to how resampling, one way that resampling is done with respect to regression models. And we will have a whole section on regression models with the Bootstrap hopefully next week. This is what's called model-based resampling. Okay, let's talk about, let's go to page 75. I'll let you answer the question on your own. You can always look at my answer to the question in the Word file. Okay, so now I've taken my resamples, I calculated my test statistic for every single resample, I know what my observed value of my test statistic is, now I need to calculate a p-value. So again, in the context of one of the drawings that we saw earlier, we were just doing a simple sample mean. Here were the y tilde bars stars, and let's say my y bar falls right there. I want an actual p-value now. How can I do that? Well, what I need to do in a non-bootstrap setting, what you're doing is this. Suppose your statistic that you're calculating is just simply called t. It could be anything. I don't care what problem it could be -2 log lambda for a likelihood ratio test, for example. And let's say, just to make this simple for now, that only large values of t indicate evidence against the null hypothesis. Okay, so we have essentially a right tail test. Then in that particular setting, your p-value will be the probability that your random variable t is greater than or equal to whatever you observe your statistic to be, given your sample is coming from f0. So for example, if t was equal to y bar, one way to calculate a regular old p-value will be just simply to take the probability that t is greater than or equal to 3, given f0. Okay. Please note that there are some typos. I noticed when I was going through my lecture last night that there are some typos. So make sure you add this little part there. And any place you see blue, make the corresponding changes. Okay, so with the bootstrap itself, we want to estimate this p-value calculation. And the way that we estimate it is as you kind of expect, the plug-in principle. The probability that t, my random variable t, is greater than or equal to the observed value of t, given my samples coming from f hat 0. That's the p-value, that's the bootstrap p-value. And I need to estimate that through Monte Carlo simulation. Now note, corresponding to the notation I was discussing earlier, where there's actually two sets of notation, this is where I think it's easier to use this kind of a notation then. Now I'm going to talk about a probability star of t stars greater than or equal to t, meaning that the distribution of t star itself is actually under the null hypothesis. So that's why I have a little subscript h0 there. How do we approximate this? It's kind of what you would expect. If I come up here to my distribution, I want to find essentially, if I could find the area underneath the curve, I want to find basically, what proportion of observations of these y tilde star, what proportion of my resampled test statistic values are greater than y bar. And this is done through this expression here. Take 1 plus the number of your t stars that are greater than or equal to t all over your number of resamples plus 1. That's the bootstrap p-value. Okay. Well, essentially what we're trying to do is calculate a proportion. So why don't I just simply maybe take this is my numerator and this is my denominator? Some people do that. Here's justification though for why using those plus ones there. The r plus 1 in the denominator, well, if HO was true, then and of course you make that assumption for hypothesis testing. If HO was true, then your original value of t that you got from your original sample would be just simply one additional piece of information. So if I take 999 resamples, well, let's take my observed value of t as now the 1,000th, essentially, sample. Then the 1 plus then that's in the numerator itself, well, of course, t star is always, t is always at least as large as itself, essentially. So you add 1. You know, it's not really a big deal. In this class, I want you to use the 1 plus, but again, outside of this class, you will often see people just simply use that to calculate a straight proportion. Is it really going to make a difference with the bootstrap, though? No, because R is always going to be large. Where does it make a difference? Well, if I want to replicate, let's say, what maybe the boot function's doing by using essentially by-hand calculations of programming in everything hardcore myself into R, then that's when it makes a difference, because I want to be able to duplicate the exact same results. So Davison and Hinckley, they use the 1 plus. That's another reason why I chose to keep that. Okay. Well, please, in this area that you see in blue here, make sure you make the same kinds of changes that I had made previously on the previous page. Basically, I was using poor notation, and we don't need the given f hat 0 there. You put a star here, you put a HO there. Okay, so there's many times when you're doing hypothesis testing where both large and small values indicate evidence against the null hypothesis. So in that case, you often say you have a two-sided test. Well, how can you calculate a p-value in that particular case? Well, again, what you're looking for is a measure of the extremeness of your observed value of your test statistic relative to the distribution itself. And so again, if I had a histogram here, and let's say that my test statistic, my observed value fell here, what you're essentially looking for is, well, how extreme is t relative to the right side of the distribution? How extreme is it relative to the left side of the distribution? Since it's a two-sided test, you need to take 2 times that corresponding measure of extremeness, that probability. So if you find this confusing at all, look back to what you would do like with the t distribution, and using a t-distribution for a hypothesis test for a mean. And so with the bootstrap, what we're going to do is simply find what's essentially the proportion of observations that are greater than or equal to, the proportion of the t stars that are greater than or equal to t. Also find the proportion of t stars that are essentially less than or equal to t. Find the smallest one of those, because that will tell us what is the measure of extremeness. Because the smaller that number is, the more extreme it is. So this is a two-sided test, multiply it by 2, and there's your p-value. I guess a short answer question on test might be to explain why do we use this as a p-value. Now there's another form of the p-value that could, another expression of the p-value that could be used. You see this sometimes, but it's not as good, and I rarely would ever use it. And that is this. Calculate the absolute value of t star. Look at and compare that to the absolute value of t itself. And essentially find a proportion. Now this can work well if your distribution is fairly symmetric about 0. Think about what's happening with that absolute value then if you have a distribution that's essentially symmetric about 0. If your distribution, let's say, is not, in particular, let's suppose that you can only observe positive values of your test statistic. So while t star has a discrete distribution itself, I'm going to draw it as a continuous because I think it's easier to see. So here's 0, and maybe this might be like a gamma distribution. Oops, think of it as a gamma distribution. Of course, you would not go below the y equals 0 line. And let's say that your test statistic falls right here. Okay? And look what you're doing here. You're calculating the absolute value of everything. Of course, that's not going to affect anything because everything's always positive. And what you're essentially doing is calculating this probability. Well, that probability is going to be large. But look how extreme you are. If it was actually a two-sided test, you will not reject HO when you should. So that's why using this kind of expression is better. Because that would capture it when you calculate the area right here, take it times 2, you're going to get a small value. So that's the problem with doing something like this. Again, a potential short answer question on test. Okay, so let's take a look at an example. Sure, those of you who took my Stat 875 class, you probably thought, I'll never have to see this Larry Bird problem again. Well, you do get to see it again. If you haven't seen this problem before, let me give you just a brief description. So Larry Bird is one of the best basketball players ever in the history of the NBA. He was actually well known for his free throw shooting. I guess lifetime or I guess career-wise, he shot about 90% or so in terms of successes. And free throws, typically, not always, but typically are shot in pairs. So you shoot one free throw, and then immediately you shoot a second free throw. And so what this data here then represents in this contingency table format is, well, what happened on the first attempt? What happened on the second attempt? So 251 times, Larry Bird made the first free throw and then also made the second free throw. 285 times he made the first, where you don't care what happened on the second free throw. Now, what's of interest with this kind of data then is to determine is what happens on that second free throw, is that independent or dependent upon what happens on the first free throw? Now, if you're a basketball fan, you might be thinking, okay, if Larry Bird misses that first shot, that might cycle himself out. And he might be more likely to miss the second free throw because of that. Well, that could be like a research hypothesis. And we can test, is there evidence to indicate that that is true? We can test that through using what's called a Pearson chi-square test for independence. So here are the hypotheses then. The null hypothesis is that the probability that my row variable, which I denote by x, the row variable's row number, let's call it I, and the column variable, its corresponding column number, that joint probability is equal to the product of the marginals. That's what independence means in the context of a contingency table. Even if you haven't had my 875 class, I would expect that all of you have seen this before. It would be first covered real briefly, perhaps in like a Stat 801. So the alternative hypothesis is that you don't have equality for all rows and all columns. So if I wanted to test this then in R, I'll try to go through this quickly because that's really not the purpose of. If I want to test this using conventional methods in R, what I can do is I can enter my contingency table into R using the array function. My cell counts go into my data argument. I'm just putting into my joint cell counts. I don't need my marginal counts. I need to specify the dimension of my contingency table as 2 by 2. And also I'm going to put some nice names on my contingency table for the rows and the columns. I put then an object called c.table for contingency table. And there's my contingency table in R. Try to do that in SAS. Good luck. Now, in order to do my test, eventually for the bootstrap, I need to transform the data to a data frame format. So what I need to do first of all is tell R, this is actually a contingency table. Before I define it as an array, so if I say as.table, it says, okay, yes, it is a contingency table, truly. And then also say, treat it as a data frame. And if I put that into an object called set1, this is what I get. So just you can almost say it unwraps that contingency table, so that every row is essentially a cell in that contingency table. But I need to go one step further. What I need to do is come up with what I like to call the raw data, meaning that every row my data frame is going to be like one observation. So one set of first and second free throw pairs. I'll let you look at the details of how to do this on your own. It's contained right there. I'm just going to go ahead and run it. And so we can see what happens is I essentially, for the 251 times he made the first and made the second attempt, I essentially will create 251 rows. For the 5 times he missed the first and missed the second, I create, at the end of my data frame, 5 rows. So in total, if you look at my, if I go back to my Word document here, so in total I have 338 different first and second free throw pairs. What that means then is, if I do n row set 2, I have 338 rows. Okay. Is everyone comfortable with the structure of the data here? This is the structure I need for the bootstrap. I don't need it to do a regular old Pearson chi-square test for independence, but I will need it for the bootstrap. Any questions? Okay. So to do a Pearson chi-square test for independence in R, do chi-sq.test. It's one of many different ways to do it. For your x argument, you put in the basically the rows. You know what happened on the first attempt, and then for the y argument, you put in, well, what happened on the second attempt. Correct equal false. Make sure that you get the regular old Pearson chi-square test for independence rather than something that's slightly adjusted. Okay, I realize I didn't actually introduce you to Pearson chi-square test. I expect all of you have seen it before, but just in case, since it's not necessarily a prerequisite for this course, here's what x squared, the Pearson chi-square test statistic, looks like. What you do is you sum over all the rows, you sum over all the columns. N sub ij denotes the cell count for row I, column j. Mu hat sub ij is what you would expect n sub ij to be under the null hypothesis. Ends up being the row total times the column total divided by the sample size. You square it, and you divide by the estimated expected value once again. Okay, so if I remove some of the marks there. So what's going to happen to this quantity if the null hypothesis is false? What's going to happen to the numerator? It's going to be so big. This is going to be big because n sub ij is going to be far away from mu hat sub ij. So what we look for with x squared is large values. Large values indicate evidence against the null hypothesis. Okay, well, how large is large? That's where then the distribution comes in. The probability distribution comes in for x squared. Now, the exact probability distribution of x squared is actually discrete. It's a discrete distribution. Instead, what we do is we use asymptotics to approximate this distribution. One can show that x squared converges in distribution to a chi-square random variable, which I'm just going to denote as a, for the lack of a better letter, where the degrees of freedom is I minus 1 times j minus 1. Now, all these derivations are actually done under the null hypothesis. Also, this convergence in distribution part here. Come on, there we go. That relies essentially as n goes to infinity. So over there, n goes to infinity. Just a quick little side note. So my 5-year-old son again here today, I think I mentioned in this class how he says he's counted to infinity 3 times. Today he asked me before he went to kindergarten, he says, "Daddy, what's infinity minus 28? I said, "It's infinity." I said, "Really?" I said, "Yeah." And I said, "Well, anytime you do that, because infinity is just a number you can't define." And he said, "Daddy, you know I have counted to infinity before." And he said, "You know that should be put in the newspaper." So again, this distribution is under the null hypothesis. This is under the fact that as n goes to infinity, this is the distribution. For fixed n, though, x squared does not have a chi-squared distribution. But we make this approximation. And then as a way to judge, well, how extreme do I have to be in terms of x squared relative to the distribution? How extreme do I have to be before I can say, yes, you know, the null hypothesis is probably false because my x squared is just so unreasonable. That's where the 1 minus alpha quantile comes in from the chi-square distribution. My p-value then is the probability that a chi-square random variable a is greater than the observed value of x squared. Okay, so a question that is often of interest then is, well, is my n large enough for this chi-squared to work? Well, you know, there's been a lot of research in that. In fact, one of the people who have researched this, if you have my 875 class, I probably mentioned this before, and that is that my academic grandfather was one of the people who researched this kind of stuff. Ken Kaler, who's the department head at Iowa State in their Department of Statistics, he did this in the 70s. It was research even before then who did that. People who did this too. And they basically found that, you know, you don't necessarily need to look at n directly. Instead, focus on the estimated expected cell counts. If they're greater than 1, you should be fine. But some people say, well, if you're greater than 5, you should be fine for the estimated expected cell counts in the null hypothesis. You should be fine in terms of a chi-square distribution would do a nice approximation to the distribution of x squared. Okay, as I had actually ran before, here is my observed value of x squared from the chi-sq.test function is 0.2727, and my p-value is 0.6015. So in other words, probability that a is greater than 0.27 is 0.6015. Okay, what does this mean? Well, there's not sufficient evidence against the independence of Larry Bird's first and second free throw outcomes. Okay. Now, finally, let's talk about the bootstrap. I guess this is a good example of, well, you know, I expect most of you have seen this, you know, seen a chi-square test like this before. You know, it's not necessarily a requirement of the class to do that, and it takes a while to explain these problems before you can actually get to a problem where you can actually apply the bootstrap. And this is a simple problem. So, what should we calculate for every single resample? Well, how about we just simply calculate essentially x squared? Why? Well, you might remember from me mentioning this before. The bootstrap often works better when you're working with a pivotal statistic. Is x squared exactly pivotal? No. But we know asymptotically it is. For a fixed, how do I say that? A fixed table size, contingency table size. In other words, the row number is fixed, the number of columns is fixed too. That's going to be actually an important thing coming up. That this is asymptotically pivotal for a fixed size contingency table. So how can we do this resampling then? So we know what statistic we're going to calculate for every resample, but we need to resample under the null hypothesis. There are actually two different ways to do this. And this was actually on my PhD comprehensive exam, too. Let's look at method number 1. Independently resample with replacement your first free throw outcomes. Sample them with replacement independently, the first free throw outcomes and the second free throw outcomes. So imagine, let's say, you have essentially 2 columns of data in that data frame. I want to resample these guys here independently of how I resample these guys. If I do my resamples like that, I have resample under the null hypothesis. Because again, think about what that means is, what happens over here, in terms of what I observe from my data, is not going to affect what happens over here. That's why it's under my null hypothesis. Essentially, what you're saying is that x, remember that's my row variable, has its own marginal distribution, which for some reason I decided to call a again. That's not the same a as what we had a few pages before for the chi-square distribution. It's just a generic way to say, hey, I have some distributions called a. And it also says that my column variable has its own marginal distribution, b. And again, look what we're saying here for the null hypothesis. The product of probabilities from the two marginal distributions leads to the joint, essentially a joint probability from a joint distribution. That's why I can do this under the null hypothesis. Okay. And what we do is we actually resample from the corresponding EDFs for both of those distributions. So the 338 values that we had for the first free throw, the 338 values that we have from the second free throw. So here's a question then for you. Name that distribution for for what A and B would be. Distribution, it's actually a named distribution binomial. That's it. So it's a binomial where you put the, let's say, the observed proportion of makes essentially as your probability of success parameter. That's all you do. You have a separate one for the rows. You have a one for the rows and you have a separate one for the columns of that table. That's it. So it's kind of cool how this all, even though we're doing everything non-parametrically, everything ends up coming down to an actual name distribution. Second, find the expected counts under independence. That should be the estimated expected counts under independence. So of course, you had to calculate those for the statistic itself. Okay, so we got 4 counts. Put those, transform those counts to probabilities. And how do you do that? Just divide by your total sample size. We'll call those pi hats. So now we have 4 probabilities. These 4 probabilities are estimated on the null hypothesis. And what we can do is go back to a multinomial distribution. A 4-category multinomial distribution. And use that to come up with new cell counts. Yes.
So our 4 categories are made, missed.
Yep. Those 4 categories. So you have a 4-category multinomial distribution. If you have my Setting 75 course, relate this back to the different ways that you can come up with a contingency table in terms of sampling. You could do independent binomial sampling. You could do multinomial sampling. Those are 2 different ways, where essentially all your contingency table counts fit into one multinomial. You could also use a Poisson as well, in a hypergeometric. Okay, so your resamples then just come directly from this multinomial distribution. That's it. Due to time restrictions, we're not going to be able to show how to do that. But if you want to see it, pages 150 to 151 of my book discuss how to do that. Now, you don't need to necessarily buy the book to see it. You can go to my book's website. Just go to my main webpage for all my websites. You'll see the link to it. Get this program out, fiber.r. It talks about an example. You can also look at my Chapter 3 lecture notes for my corresponding course to see how that's done. Okay. So, we are out of time. Are there any questions? Okay, that's it for today.